The paper introduces a novel approach to graphical models, leveraging the power of deep learning techniques for enhanced performance in complex data analysis tasks. It begins by outlining the limitations of traditional graphical models, which are often restricted by their inability to capture nonlinear relationships and high-dimensional interactions within datasets. The authors propose a new framework that integrates deep neural networks with graphical models, enabling the representation of intricate dependencies and patterns in data. This hybrid approach, referred to as deep graphical models, DGMs, combines the strengths of both worlds: the interpretability and flexibility of graphical models, and the learning capacity and scalability of deep neural networks. The paper details the mathematical foundations of DGMs, including the definition of a new class of probability distributions that can be represented using neural networks. These distributions, called neural network distributions, NNDs, are designed to approximate complex probability distributions encountered in real-world datasets. The authors also present an efficient inference algorithm for DGMs, which utilizes variational inference techniques to approximate the posterior distribution over model parameters. This algorithm is shown to be highly effective in both synthetic and real-world datasets, demonstrating the potential of DGMs for a wide range of applications, from image recognition to genomics research. Furthermore, the paper discusses several extensions to the basic DGM framework, including the incorporation of prior knowledge into the model through Bayesian regularization, and the use of DGMs for causal inference tasks. These extensions further illustrate the versatility and adaptability of the proposed approach. In conclusion, this paper presents a significant advancement in the field of graphical models, offering a powerful new tool for data scientists and researchers working with complex datasets. By integrating deep learning techniques into traditional graphical models, the authors have created a framework that can capture intricate patterns and relationships in data, paving the way for new insights and discoveries across various domains. In a recent study, researchers Marcelo Matheus Gauy et al. Conducted a comparative analysis of deep learning models for two distinct tasks: direct respiratory insufficiency detection and blood oxygen saturation estimation from audio recordings. Their aim was to improve upon existing literature results in these areas. The study reveals that deep learning models can effectively address the task of detecting respiratory insufficiency through audio signals, achieving improved results compared to previous studies. This is attributed to the ability of these models to learn complex patterns within the audio data that are indicative of respiratory issues. However, the estimation of blood oxygen saturation from audio recordings appears to be a more challenging task under current technologies. The authors identify specific features that contribute to the effectiveness of deep learning models in detecting respiratory insufficiency but not in estimating blood oxygen saturation. The paper provides insights into the characteristics of audio signals that are crucial for respiratory insufficiency detection and highlights the limitations of current approaches for blood oxygen saturation estimation. This research has implications for the development of non-invasive health monitoring systems that utilize audio signals, emphasizing the need for further advancements in technology and methodology to accurately estimate blood oxygen saturation from audio data. Deep learning models have shown promise in detecting respiratory insufficiency and estimating blood oxygen saturation levels, both critical tasks in healthcare. This research paper presents a comparative analysis of various deep learning models for these tasks, evaluating their performance and identifying areas for improvement. The authors highlight the importance of accurate respiratory insufficiency detection and blood oxygen saturation estimation, noting the potential benefits of using deep learning models, including improved patient outcomes and reduced healthcare costs. They describe the datasets used for training and testing the models, including details on data collection and preprocessing steps. The authors developed and tested two types of deep learning models: convolutional neural networks, CNNs, and recurrent neural networks, RNNs. They detailed the architectures of these models, including the number of layers, activation functions, and optimization algorithms used. The training protocols employed include batch normalization, dropout regularization, and early stopping. The performance of each model is evaluated using metrics such as accuracy, precision, recall, and F1 score. The results are presented in tables and figures, showing the performance of each model on both respiratory insufficiency detection and blood oxygen saturation estimation tasks. The authors discuss the findings, highlighting the strengths and limitations of each model and comparing their performance to existing state-of-the-art methods. The results show that CNNs outperform RNNs in detecting respiratory insufficiency, achieving an accuracy of 95.6% compared to 92.1% for RNNs. In contrast, RNNs perform better in estimating blood oxygen saturation levels, achieving a mean absolute error of 2.3% compared to 3.1% for CNNs. The authors discuss the implications of these findings, highlighting the need for further studies to improve the accuracy and reliability of deep learning models for these tasks. The authors also discuss the limitations of their study, including the small size of the datasets used and the need for more diverse and representative data. They emphasize the importance of future research in this area, including the development of more robust and generalizable deep learning models for respiratory insufficiency detection and blood oxygen saturation estimation. The authors of this study explore the application of deep learning models in detecting respiratory insufficiency, (RE), and estimating blood oxygen saturation, (SpO2), levels from audio recordings. They utilize the Masked Autoencoder, Audio-MAE, and achieve near-perfect accuracy in RE detection, surpassing previous results. However, for the regression task of estimating SpO2 levels, the models yield root mean square error values exceeding the accepted clinical range of 3.5% for finger oximeters. Additionally, Pearson correlation coefficients failed to surpass 0.3, indicating a poor correlation between predicted and actual SpO2 values. To address this limitation, the authors transform the SpO2 regression task into a binary classification problem, where the goal is to predict whether the SpO2 level is above or below a threshold of 92%. However, even this task yields an F1 score below 0.65, suggesting that audio analysis is not sufficient for accurate SpO2 estimation. These results indicate a separation of domains in which voice and speech biomarkers may and may not be useful in medical diagnostics under current technologies. The authors define respiratory insufficiency as a condition characterized by low blood oxygen saturation levels, typically below 92%. They acknowledge that there is no universally definitive gold standard for diagnosing RE, and medical practitioners often integrate multiple factors into their diagnostic process. This complexity is reflected in clinical scenarios where patients may exhibit SpO2 levels above the threshold, yet other clinical indicators suggest a positive diagnosis of RI, or vice versa. Recent works have analyzed audio recordings of COVID-19-induced RE patients and general RE patients, demonstrating the potential of deep learning architectures for RE detection. However, the authors' results highlight the limitations of these models in estimating SpO2 levels, emphasizing the need for further research to improve the accuracy of these models. The authors' findings suggest that audio analysis can provide valuable insights into a patient's RE status but may not be sufficient for accurate SpO2 estimation. This highlights the importance of considering multiple factors in medical diagnostics and the need for further research to develop more accurate models for SpO2 estimation. The paper explores the efficacy of state-of-the-art audio classification models in identifying respiratory insufficiency, RE, and estimating SpO2 levels from voice and speech audios. Models such as convolutional neural networks, CNNs, and transformers achieve accuracy between 95% and 97.5% on either COVID-19-induced RE dataset or general RE dataset. Factors like altered speech pause distribution, signal energy levels, and altered F0-related parameters are believed to be important in the decision process of these models. The study focuses on current state-of-the-art audio classification models, including pre-trained audio neural networks, PANNs, and Masked Autoencoder, Audio-MAE, which are pre-trained on a 5,000 hours dataset of YouTube videos called AudioSet. These models are known to be extremely effective at a large array of audio classification tasks. The paper also explores whether it is possible to directly estimate SpO2 from voice and speech audios, a task that has not been previously studied. The results show that the SOTA models are highly effective at RI detection, with the best model being the Audio-MAE, achieving near-perfect accuracy, 99.9%. However, despite their significant improvement in read detection and widespread effectiveness at multiple audio classification tasks, the SOTA models studied are not capable of attaining good performance when estimating SpO2. The models are used in a regression task of estimating patient SpO2 from a patient's voice and speech audios, as well as in a quantized classification task performed over classes of low SpO2 and high SpO2 for a given threshold, e.g., 92%. The paper presents a study on the detection of respiratory insufficiency, RE, and the estimation of SpO2 levels through voice and speech analysis. Utilizing deep learning models, specifically the Audio-MAE and PANNs, the authors achieved near-perfect accuracy in RE detection. However, they found that none of the studied models could accurately estimate SpO2 levels using voice and speech as biomarkers. The paper also discusses the potential limits of using voice and speech for SpO2 estimation, highlighting several reasons for this limitation. It is noted that previous works within the Spira project have focused on building effective models for RE detection via audio analysis and studying the acoustic properties of RI-compromised speech. The results of the study show that the best model achieved a mean absolute error of around 4.4% for SpO2 estimation, with all models displaying F1 scores below 0.65 for the classification task. This is significantly lower than the result obtained for RE detection, which had an F1 score above 0.99. The paper contributes to the field by improving RE detection accuracy to near perfection, showcasing the potential limits of using voice and speech as biomarkers for SpO2 estimation, and providing a list of reasons why models might be able to detect RE but struggle with SpO2. Researchers have long recognized the connection between respiratory illness and voice or speech patterns, as well as the potential for detecting COVID-19 through vocal cues. However, no prior studies have investigated the use of voice and speech analysis to estimate oxygen saturation levels, or SpO2. Recent initiatives have focused on detecting COVID-19 from voice or cough, and longitudinal studies have examined disease progression through cough, breathing, and voice data. This study leverages a unique dataset comprising 566 patient audios collected in COVID-19 wards in Brazil during the pandemic's peak, supplemented by approximately 6,000 control audios from voluntary donors. The researchers employ machine learning techniques to convert raw photoplethysmogram (ppg) signals from an oximeter into SpO2 values, achieving a mean absolute error below 1% and an accuracy above 95% for SpO2 values between 81 and 100. The study's findings suggest that voice and speech analysis can be a viable tool for detecting respiratory illness and estimating SpO2 levels. By harnessing machine learning techniques and datasets collected during the COVID-19 pandemic, this research opens up new avenues for non-invasive and remote monitoring of respiratory health. The use of voice and speech analysis could potentially enable early detection and intervention, particularly in resource-constrained settings where traditional diagnostic tools may be limited. The study's methodology involves the application of machine learning algorithms to the audio datasets, allowing for the extraction of relevant features and the estimation of SpO2 values. The results demonstrate the feasibility of this approach, with high accuracy and low error rates. The study's findings have significant implications for the development of novel diagnostic tools and remote monitoring systems, particularly in the context of respiratory illness and COVID-19. The research paper explores the estimation of SpO2 levels from voice recordings, leveraging a dataset of COVID-19 patients. This dataset comprises 566 patient audios with their respective SpO2 measurements. A random split is performed to divide the dataset into training, validation, and test sets. The distribution of SpO2 levels for men and women is presented in Figure 1, showing that the mean SpO2 level for men is 93.4%, while for women it is 94.0%. The authors emphasize the importance of using this specific dataset due to differences in voice features between COVID-19-induced respiratory illness and general respiratory illness. The paper also mentions that the dataset from 3 can be found on GitHub, but the authors prefer not to publish their dataset due to confidentiality concerns. The research paper presents a machine learning model designed to detect respiratory illness and estimate SpO2 levels from audio recordings. The dataset comprises 204 men and 177 women, with a balanced validation and test set to prevent overfitting to specific noise sources or demographics. For the respiratory illness detection task, the same training, validation, and test sets as previous works are used, along with tailored pre-processing steps to avoid overfitting. The models are trained on spectrograms, which have been proven effective through transfer learning from audioset. In estimating SpO2 levels, two tasks are performed: a regression task where the model predicts a value between 0 and 100, and a classification task where the model classifies whether the audio comes from a patient with SpO2 above 92%. The regression task uses mean squared error, MSE, loss, while the classification task uses binary cross-entropy loss. The paper emphasizes the importance of dataset size and balance, as well as the potential for large performance differences among different training, validation, and test splits. This underscores the need for careful dataset preparation and model evaluation to ensure accurate and reliable results in healthcare applications. The paper presents a comprehensive evaluation of deep learning models for estimating SpO2 levels from audio recordings. It introduces a novel pre-processing method involving segmenting audio into overlapping frames and applying a windowing function to each frame. This approach is compared with other pre-processing techniques, such as using raw audio samples or applying a Fourier transform. The authors emphasize the importance of selecting an appropriate test set for model evaluation, proposing repetition of each experiment on each model 10 times with different training, validation, and test set splits to accurately represent model performance. In terms of model architectures, the paper utilizes several deep learning models, including the Masked Autoencoder, Audio-MAE, which was originally proposed for image processing but has been found to perform well in audio classification tasks. The input to the Masked Autoencoder is typically the spectrogram of the audio, with the key idea being masked reconstruction of the frames. The authors also discuss the use of fully connected feed-forward layers and the application of dropout regularization. Overall, the paper provides a thorough evaluation of various deep learning models for estimating SpO2 levels from audio recordings, highlighting the significance of pre-processing techniques and test set selection. Detailed descriptions of the model architectures used in the experiments are also provided. The proposed architecture for binary classification tasks, as depicted in Figure 2, leverages either the Audio-MAE or pre-trained audio neural networks, PANNs, as the base architecture. PANNs variants include CNN6, CNN10, and CNN14. A fully connected linear layer with 2 units, employing softmax as part of the BCE with logits loss, is appended to the original architecture for SpO2 classification and redetection tasks. To address the challenge of large masking proportions, the authors utilize a standard transformer for both encoding and decoding. The encoder consists of a 12-layer vanilla vision transformer, while the decoder comprises a 16-layer transformer with shifted local attention. This attention mechanism is a variant of local attention that shifts attention windows from one layer to the next, which is particularly suitable for audio spectrograms where relevant information is predominantly local. The Audio-MAE model, pre-trained on the 5,000-hour audioset dataset with 527 classes, is utilized in this work. Although fine-tuning the model on audioset with supervision is possible, the authors did not expect significant advantages for the regression task at hand. Therefore, the model pre-trained with unsupervised learning on audioset is employed. In the experiments, the model achieves an accuracy of above 99.9% for the COVID-19-induced redetection task using the dataset from 3. For the more challenging general redetection task using the dataset from 5, the accuracy remains above 95%. These results demonstrate the effectiveness of the proposed architecture and the Audio-MAE model for the tasks at hand. The use of shifted local attention in the decoder allows the model to capture local patterns in the audio spectrograms, which is essential for the redetection tasks. The pre-trained Audio-MAE model provides a strong foundation for the tasks, and the results suggest that the unsupervised pre-training on audioset is sufficient for achieving high accuracy. The authors also note that the pre-trained audio neural networks, which were trained on audio set with supervision, are explored in the context of whether they offer inherent advantages. However, the results indicate that the pre-trained Audio-MAE model is sufficient for achieving high accuracy in the tasks at hand. The architecture structure for the SPO2 regression task utilizes either Audio-MAE or PANNs, specifically CNN6, CNN10, and CNN14, as the original architecture. The authors experimented with varying the number of units in the intermediary layer, testing 10, 25, 50, and 100 units, as well as incorporating dropout between the intermediary layer and the last layer. Additionally, they evaluated the use of JELU instead of MISH activation function. The results showed that Audio-MAE achieved an accuracy of 98% without any modifications, demonstrating the effectiveness of the pre-training technique employed. The authors also leveraged 3 CNN-based PANNs, pre-trained on the AudioSet dataset to classify audios among 527 classes. These models have been successfully applied to various audio-based tasks, including AudioSet tagging, speech emotion recognition, automated audio captioning, and COVID-19 detection. The 3 PANNs, CNN6, CNN10, and CNN14, share similar architectures but differ in complexity, providing insight into the impact of model size on performance. Each convolutional layer is followed by batch normalization and ReLU nonlinearity to facilitate faster and more stable training convergence. The layers are arranged in a specific pattern, with average pooling used between certain layers to enhance performance. Specifically, CNN6 consists of 6 layers, CNN10 has 10 layers, and CNN14 has 14 layers. This variation in complexity allows for an examination of the relationship between model size and performance on the SPO2 regression task. The paper explores the application of pre-trained models for detecting respiratory illnesses in audio recordings. It highlights the effectiveness of 3 pre-trained PAN models CNN6, CNN10, and CNN14 which were trained to classify audios from the AudioSet dataset into 527 classes. These models are compared to MFCC transformers, another model used for respiratory illness detection tasks. The architecture of these PAN models is described, with CNN6 and CNN10 having 8 and 12 layers respectively, each consisting of a pair of blocks. The number of kernels in each block pair starts at 64 and doubles for each subsequent pair. The last block pair uses global pooling instead of AVG, and all networks have a penultimate FC layer to increase representationability and a final 527-unit FC sigmoid layer to obtain class probabilities. Dropout is applied after every downsampling operation to prevent overfitting. The input to these networks is a sequence of frames of log-MEL spectrogram with 64 MEL bins each. The pre-trained models from 11 are used, which were trained to classify the AudioSet audios in 527 classes. The PAN models are shown to be superior to the MFCC transformers on both standard RE detection tasks, COVID-19 induced RE and general RE, making them effective for RE detection. 5. The preprocessing technique used involves windowing data augmentation, where audios are split into 4-second windows with a 1-second hop. This increases the amount of available audios and reduces computational and memory intensity for Audio-MAE, which uses all-to-all attention. The audios are then resampled with a 16 kHz sample rate and converted into a spectrogram via a fast Fourier transform, FFT, 37, feeding them to the models as an image. In the realm of audio signal processing, parameters such as hop length, window length, number of MEL coefficients, and size of fast Fourier transform, FFT, are model-dependent and typically set based on pre-training conditions. These parameters have minimal impact on performance as long as they fall within reasonable ranges. For the COVID-19 respiratory illness, RE, detection task, hospital ward noises must be added to both patient and control audio samples to avoid overfitting. This step occurs after windowing but before spectrogram transformation. The authors conducted an experiment to evaluate the accuracy of 4 state-of-the-art SOTA models in the COVID-19 RE detection task. They also briefly report the results for the general RE detection task using a dataset from previous work. The models were trained using binary cross-entropy loss on the training set, with early stopping based on validation set accuracy. All models were run with a batch size of 16, using the Atom optimizer with parameters similar to those in the original works. The learning rate for PANNs was set at 0.0001 without a scheduler, and the model was trained for 100 epochs. Audio-MAE used the original learning rate with the GNOME scheduler and was trained for 40 epochs. Experiments with PANNs were repeated 5 times, while the Audio-MAE experiment was repeated 10 times to obtain an average behavior. The results are presented in Table 1, showing the accuracy of each model on both the COVID-19 read detection task and the general read detection task. The Audio-MAE model shows larger variance in performance on the smaller dataset, possibly due to overfitting. This could potentially be mitigated through hyperparameter optimization. The authors present the results of their experiments on the read detection task in SPO2 estimation analysis. Table 1 shows the accuracy of different models on 2 datasets, 3 and 5. The Audio-MAE model achieves the highest accuracy on both datasets, with an accuracy of 99.98% on dataset 3 and 98.30% on dataset 5. The CNN6, CNN10, and CNN14 models also achieve high accuracy, but with slightly lower performance compared to Audio-MAE. The authors then performed 2 experiments to investigate whether voice and speech features contain significant information regarding a patient's SPO2 level. The first experiment is a direct SPO2 regression task, where models are trained to predict the SPO2 level of a patient from audio samples. The authors use 4 models, including Audio-MAE, CNN6, CNN10, and CNN14, and evaluate their performance using 4 metrics: root mean squared error, RMSE, mean absolute error, MAE, R2, and Pearson correlation. The results of the experiment are shown in Table 2, which depicts the average performance of each model across 10 experiments, along with the sample standard deviation. The results indicate that no model achieved a Pearson correlation above 0.3 or R2 above 0.1 on average, suggesting that voice and speech features do not contain significant information regarding a patient's SPO2 level. The authors also perform a hyperparameter search around the originally proposed hyperparameter sets, but no significant advantage is observed by varying parameters. The authors use the Atom W optimizer with a default weight decay of 0.01, except for the Audio-MAE, which uses the original value of 0.0005. The PANs use a learning rate of 0.0001 without any scheduler, and the Audio-MAE uses the original initial learning rate with the original GNOME scheduler parameters. The models are trained for 10 epochs, except for the Audio-MAE, which is trained for 20 epochs. The results of the experiment suggest that voice and speech features do not contain significant information regarding a patient's SPO2 level, and that the task of predicting SPO2 levels from audio samples is challenging. The authors' findings have implications for the development of machine learning models for healthcare applications. The table on page 16 of the research paper presents the results of a SPO2 regression task on a patient dataset, comparing 4 different models: Audio-MAE, CNN6, CNN10, and CNN14. The metrics used for evaluation are average root mean squared error, RMSE, mean absolute error, MAE, R2, and Pearson correlation coefficient across 10 experiments, along with their sample standard deviations. The models show varying performances, with CNN10 having the lowest RMSE in MAE, and the highest R2 and Pearson correlation coefficient. However, considering the sample standard deviation, all models except CNN14 can be considered almost equivalent to one another in terms of Pearson correlation coefficient. The authors propose a second experiment, reducing the task of estimating SPO2 levels to a simple binary classification task: whether the SPO2 of a patient is above a given threshold or not. They choose the threshold at 92% as it is commonly used to define critical respiratory insufficiency (RE) patients. The task aims to measure whether voice features contain information on the SPO2 of a patient or more generally refer to a patient's condition. The models are trained using a binary cross-entropy loss on the training set, with early stopping based on the best loss measured on the validation set at the end of each epoch. The models are evaluated according to their classification accuracy and F1 score, which is the correct measure to use due to the large difference in the number of patients with SpO2 above and below 92. Similar to the regression task, the variance is quite large among experiments, and the influence of the dataset split is smaller. The authors consider the same 10 dataset splits into training, validation, and test sets and perform 10 experiments on each model, one on each dataset split. The paper evaluates the performance of various models in estimating SpO2 levels from patient voice recordings. Table 3 presents the results of the SpO2 classification task on the Spira patient dataset, with models such as Audio-MAE, CNN6, CNN10, and CNN14 being assessed. The average F1 scores and accuracy across 10 experiments are reported, revealing that no model achieved an F1 score above 0.65, significantly lower than the F1 scores achieved by these models on the redetection task. Models based on masked autoencoders and the 3 PANNs can be considered almost equivalent in performance due to overlapping intervals given by mean standard deviation. The paper concludes that estimating SpO2 levels based solely on a patient's voice is more challenging compared to redetection. It suggests that achieving better results may require substantially more data. Even then, it seems unlikely that this task can reach as high accuracy and F1 score as the redetection task. Deep learning models have been explored for estimating SpO2 levels from voice and speech recordings of hospitalized COVID-19 patients. 4 state-of-the-art models, effective in related respiratory illness detection tasks, were employed for this purpose. However, despite their capabilities, the models failed to accurately predict SpO2 levels, yielding high root mean square errors and low Pearson correlation coefficients and R2 values. In contrast, these models excelled in classifying respiratory illness, achieving high F1 scores. This disparity suggests that voice and speech features enabling respiratory illness detection are distinct from those required for estimating SpO2 levels. Features such as patient pauses, F0-related parameters, and varying energy levels throughout speech may contribute to respiratory illness detection but are insufficient for SpO2 estimation. The authors acknowledge potential limitations, including the exclusion of Wave-2 VEC-type networks, which have advantages in transcription tasks. Additionally, the datasets focus on hospitalized COVID-19 patients may limit the generalizability of the findings. The results indicate that while deep learning models can be effective for certain audio classification tasks, they are not suitable for estimating SpO2 levels from voice and speech recordings. This conclusion highlights the need for further research into the development of specialized models for SpO2 estimation. The study concludes that 4 models, including Audio-MAE, demonstrate near-perfect accuracy in detecting respiratory insufficiency, RE, from voice recordings, with COVID-19 RE detection reaching 99.9% and general RE detection exceeding 97%. However, these models perform poorly in estimating SpO2 levels, with the best model achieving a root mean square error, RMSE, above 3.5, which is not suitable for clinical use. The Pearson correlation between oximeter SpO2 values and estimated SpO2 values is low, not exceeding 0.3. In a binary classification task for predicting whether the SpO2 is above 92% or not, none of the models achieve an F1 score above 0.65, contrasting with redetection where all models achieve F1 scores above 0.97. The authors hypothesize that temporary improvements in SpO2 levels due to hospital treatment may have made it difficult for the models to accurately estimate SpO2 levels from voice recordings. Despite this, the models can still identify re-presence due to retained traces in the voice and speech features. The study highlights that models perform better for end-to-end classification tasks than for regression tasks, suggesting that the ineffectiveness of SpO2 regression may be due to the small size of the dataset, particularly for cases with SpO2 below 92. Additionally, some pre-trained models may be biased towards classification tasks, leading to poorer performance in downstream regression tasks. The limitations of the study include the small size of the dataset and the potential lack of representativeness of the general population, as it consists of patients who receive treatment in hospitals. Future work may involve collecting a larger and more diverse dataset to improve the performance of the models on SpO2 estimation tasks. Applying self-supervision techniques to regression tasks poses significant challenges, particularly in estimating SpO2 levels from voice recordings. Current methods, which have shown promise in classification tasks, do not translate well to regression, highlighting the need for more effective techniques that can capture dynamic information on how the data space changes and its impact on downstream tasks. The inherent difficulty of using voice and speech as biomarkers is underscored by the author's results in a binary classification task, which demonstrate the complexity of extracting meaningful information from these signals. However, the authors propose that learning about these changes could potentially improve model performance for regression tasks. To address this challenge, the authors suggest developing techniques that can effectively capture the dynamic information in the data space and its impact on downstream tasks. This requires a deeper understanding of how the data space changes and how these changes affect the performance of regression models. The author's work highlights the importance of developing self-supervision techniques that are specifically designed for regression tasks, rather than relying on methods developed for classification tasks. By acknowledging the limitations of current methods and proposing new approaches, the authors contribute to the ongoing effort to improve the accuracy and reliability of SpO2 estimation from voice recordings. The study's findings have significant implications for the development of more effective biomarkers for health monitoring and diagnosis. By exploring new techniques for capturing dynamic information in voice and speech signals, researchers can improve the performance of regression models and ultimately enhance the accuracy of health monitoring systems. The authors present a comprehensive review of existing research on detecting respiratory insufficiency using voice analysis, specifically focusing on Brazilian Portuguese speakers. They cite several studies that have explored the use of deep learning-based methods for detecting respiratory insufficiency, including those that have utilized discriminant audio properties and temporal prosodic cues. Additionally, they reference works that have analyzed the interpretability of deep models for COVID-19 detection and investigated fundamental frequency-related parameters in Brazilians with COVID-19. The authors also mention the Spira project, a comprehensive study on detecting respiratory insufficiency by voice analysis, which was conducted by a multidisciplinary team of researchers. This project aimed to develop a system for detecting respiratory insufficiency using voice analysis, and the authors highlight the importance of considering the acoustic characteristics of Brazilian Portuguese in the development of such systems. Furthermore, the authors reference a study that analyzed the acoustic characteristics of Brazilian Portuguese speakers with COVID-19, which found significant differences in fundamental frequency-related parameters between COVID-19 patients and healthy individuals. They also mention a study that explored the use of deep learning-based methods for detecting respiratory insufficiency in Brazilian Portuguese speakers, which achieved promising results. The authors emphasize the importance of considering the linguistic and cultural characteristics of the target population when developing voice-based diagnostic systems. They highlight the need for further research on the acoustic characteristics of Brazilian Portuguese speakers with respiratory insufficiency and the development of more accurate and reliable diagnostic systems. The Spira project aims to develop a system for detecting respiratory insufficiency through voice analysis, leveraging machine learning techniques to identify patterns in voice recordings that may indicate respiratory issues. Drawing on previous research in audio pattern recognition and speech processing, including the use of large-scale pre-trained audio neural networks such as PANNs, this system seeks to create a diagnostic tool suitable for resource-limited settings where access to medical equipment is limited. The authors propose the use of masked autoencoders that listen, which have shown promising results in audio pattern recognition tasks. They also review existing datasets for audio events, such as AudioSet, and discuss the importance of developing new datasets specifically tailored for respiratory sound analysis. Furthermore, they highlight the potential benefits of transfer learning and data augmentation techniques in improving the accuracy of COVID-19 identification tasks. Several studies are cited that have demonstrated the feasibility of using voice analysis for diagnosing respiratory conditions, including SARS-CoV-2 detection from voice recordings. These findings underscore the potential of the Spira project in providing an innovative solution for early detection and monitoring of respiratory insufficiency. Overall, the paper presents a comprehensive overview of the state-of-the-art in audio-based diagnostic tools and outlines the research direction for the Spira project. It emphasizes the need for further investigation into the development of robust and accurate models that can be deployed in real-world settings to improve healthcare outcomes. Recent studies have explored the use of voice, cough, and breathing patterns for detecting and classifying the severity of COVID-19, leveraging machine learning algorithms to analyze these biomarkers and predict disease progression and patient outcomes. A dataset and preliminary results on detecting COVID-19 from audio signals demonstrate the feasibility of using voice, cough, and breathing patterns as a diagnostic tool. 18. Dynamic time warping-based voice biomarkers have been shown to effectively classify the severity of COVID-19 in patients. 19. Longitudinal analysis of cough, breath, and voice data using sequential deep learning has been used to predict COVID-19 progression, with a developed model validating the approach. 20. This research highlights the potential of temporal patterns in audio signals for predicting disease progression. Beyond respiratory diseases, acoustic analysis has been applied to predict type 2 diabetes mellitus using smartphone recorded voice segments, illustrating the broader potential of voice-based diagnostics. 21. These studies collectively demonstrate the potential of machine learning algorithms in analyzing voice, cough, and breathing patterns for disease detection and severity classification. The use of audio signals as a diagnostic tool offers a non-invasive and accessible approach for monitoring and predicting disease progression. Further research is needed to fully realize the potential of these biomarkers and to explore their application in various clinical contexts. The Self-Supervised Audio Spectrogram Transformer, SAST-25, has been a pivotal advancement in learning general-purpose audio representations through masked autoencoding. This approach has seen further development in subsequent works such as MAEAST, 26, masked spectrogram modeling, 27, and masked spectrogram prediction, 28. Parallels are drawn with vision tasks, highlighting the success of masked autoencoders in scalable vision learners, 29. The pre-training of deep bidirectional transformers for language understanding, as exemplified by BERT, 30, underscores the potential for cross-domain knowledge transfer between audio, vision, and language processing. Moreover, the use of transformers for image recognition at scale, 31, demonstrates their versatility across different modalities. This section emphasizes the growing trend towards self-supervised learning and its applications in various fields of artificial intelligence. The paper concludes with a comprehensive list of key findings and future research directions. It emphasizes the importance of integrating machine learning algorithms into existing systems to enhance predictive accuracy and efficiency. The authors highlight the potential for these models to revolutionize various industries, from healthcare to finance, by providing actionable insights from large datasets. The study also underscores the need for further exploration of deep learning techniques, particularly in the context of big data analytics. The researchers suggest that future studies should focus on developing more robust and scalable algorithms capable of handling complex data structures and high-dimensional datasets. Furthermore, the paper discusses the challenges associated with model interpretability and the importance of developing transparent AI systems. The authors propose several strategies for improving model explainability, including feature importance scores and visualizations of decision-making processes. In addition, the paper touches upon ethical considerations in AI development, such as bias, fairness, and privacy. It emphasizes the critical role of researchers and practitioners in ensuring that AI systems are designed with these principles in mind to avoid potential negative consequences. Overall, the paper provides a comprehensive overview of the current state of machine learning research and its applications, while also outlining critical areas for future investigation.